Thank you so much to the Osmosis team for hosting such an amazing event. I mean, this is honestly one of a kind so far. So big shout out, kudos. So I'm Amit. I'm from the Kujira core team. I'm an engineer on the Kujira core team, and I'm also the founder of Entropic Labs. I'll be talking a little bit about how we use CosmWasm on Kujira and the ways in which we leverage its composability. And then a little end section about how we foresee CosmWasm evolving to become an even safer smart contract scripting language. All right, so my background, I started working in this in Web3 back on Anchor in Terra, and then I joined the Kujira team about 2 years ago, working mostly on their core DeFi protocols, such as Ghost, their money market, kind of got a foot in everything there. I've also gone on to create my own couple of protocols, and that's what Entropic Labs is all about. Yeah, so I'm just gonna breeze through this kind of overview of CosmWasm. I'm sure we all already know how CosmWasm works, but CosmWasm follows this concept of the actor model, right? We have contracts that are executed by messages, which may optionally call other contracts. And then our contracts also have access to the Go modules of the SDK. For example, IBC or a bank module. Or on Kujira, we have a Oracle module built in as well. So first, we have to ask, why do we care so much about composability on smart contracts? So the answer is that really we want to componentize and compartmentalize as much functionality as we can, both because it's a separation of concerns, but also because each of our smart contracts are useful on their own. So we're basically bringing the Unix design philosophy to smart contract development. So I'm just going to give a couple of examples of what we already have on Kujira as core building blocks. So we have an on-chain order book, which is implemented as a single smart contract. And then on top of that, we can implement more smart contracts, such as an automated market maker. So an order book basically doesn't give you any of the nice features you have when you have some like XYK pools or stable swap pools. So we've built a layer on top of our order book, on-chain order book infrastructure that basically provides all the functionality that you'd come to expect from, for example, a Uniswap or Osmosis-like DEX. Our most, I guess, iconic product is Orca, which is a democratized liquidation queue. This is also provided as a self-contained contract and app that users use. And basically, this abstracts away all the complexity of handling liquidations and moves it basically to something that you can query and execute externally. And finally, we have a money market Ghost, which again provides a very modularized functionality so that you can easily plug into a pool of assets that you want to borrow from, and you can introduce, for example, leverage features into any protocol that can generically compose on Ghost. You can also create lending protocols and stable interests and so on by leveraging the vault functionality of Ghost. So this is the other side of Ghost. I'm going to skip over it, but this is the market interface and so on. So the key idea here is that when we are building applications on Kujira, it's really like building with Legos. So for example, I'll get to a couple of other examples, but for example, when we build margin trading, for example, we have a Fin order book for the pair. So for example, Atom USDC is a pair on Fin. But then when we want to enable margin trading on that, we can simply plug into Ghost, the money market, borrow, for example, USDC or Atom, depending on whether we want to go long or short. And then we have a single smart contract that plugs into Fin, that plugs into Ghost, and manages everything for us. So really, when we create all this advanced functionality, we're basically doing the minimum possible to enable it, and really following that Unix design philosophy. So this one is a lot more complicated. This is our leveraged LP contract. In a nutshell, what this enables is someone to provide single-sided liquidity or more liquidity than they actually own. So for example, if I have an order book, Atom USDC again, and I want to provide 10x the amount of liquidity I actually own, I can borrow from the money market, provide that on top of Bo, which is our automated market maker, receive LP tokens, and the LP tokens are held in a leveraged position. And the only real risk of liquidation there is something like impermanent loss. And the reason I bring up this specific diagram is you can see that there's a huge amount of complexity here in terms of how many different protocols that we're actually connecting to. So for example, we are providing liquidity, so we do have to connect to Bo, the automated market maker. But then to borrow from each side, we have to connect to 2 different money market vaults. And then we have 2 different paths of liquidation. Either we liquidate one asset or the other for each other. So we do have to connect to 2 different Orca instances. And the actual contract that we're dealing with that builds upon all of this is quite simple because we're all plugging into these systems. The problem now is that you have to keep track of, for example, math and all the possible liquidation mechanisms and position safety and so on. Basically, the process ends up dealing with 7 different types of tokens, ranging from the base 2 assets on the Atom USDC, for example, the A asset and the B asset of that trading pair, or the debt tokens representing the debt when you borrow, or the LP tokens representing how much liquidity you've actually provided, and so on. So there's a whole lot of different currencies that we convert between in these contracts. And so this is just a piece of code that I've actually simplified that shows some amount of calculation during our liquidation process. And does this have, this has a laser pointer. But the idea is that we're calculating some sort of liquidation rate, and then we're calculating how much debt we have and how much we can actually repay before reversing. We apply basically our liquidation rate here, and then we reverse that to figure out how much we actually need to repay. And you wouldn't know what's going on here unless you were the one who wrote it, or, and so, sorry, these are all, very untyped, relatively untyped things. So all we know that we have a decimal and we have 3 integers, and we don't know exactly what we're calculating here, right? This is a very ambiguous exchange rate. If our variables were named any less descriptively, even though they're really not named very descriptively here either, we wouldn't know what's happening. And likewise, when we have integers representing amounts, we don't know what currency that we're representing in that integer variable. So all of the currency conversion and currency tracking is completely manual in the form, usually, of doc comments or variable naming. And very quickly, you can see that you can have whole sentences as variable names. So this is just not going to scale for us internally at Kujira, but also for our smart contract developers building on top of Kujira and CosmWasm as a whole. And the worst part is that even if you're keeping track of all these things, there's no safety provided to you. If I have, for example, a currency in US dollars and a currency in euros, and I try to add them, it's not going to complain. But that operation does not make sense. So we need to manually type check everything, and this is not scalable. Another problem is that when we want to do, for example, liquidation simulations and so on, we have to specify the amounts and the rates and so on as decimals and integers in our CosmWasm contract interfaces. So the problem is that we may be using some Orca that liquidates from A to B, and we have to, again, manually keep track of which liquidation queue we're using, which order book we're submitting an order to, and whether we're using the right currency in our values and so on. So, so we have no currency checks again, and we're using arbitrarily calculated decimal values. So maybe we're providing a completely erroneous conversion rate. So that's our second problem, that the boundaries and interfaces between actors provide extra points of failure. And I say actors really because these boundaries could be between 2 contracts on the chain in CosmWasm, or it could be between a contract and, for example, an Oracle module, where the Oracle module is returning a price rate, but you don't know, which 2 assets and so on in your code that is that price is for. So, okay, let's see how we can maybe start combating this. So this is, a typical CosmWasm query message. Here, this is a very simplified interface for Orca, which is the liquidation engine. We want to simulate a liquidation given an amount of collateral and the exchange rate. How much will we receive in return after the liquidation is executed? So ideally, we'd have how much we're paying in collateral amount and receiving in the repay amount. We want that type. So you know what? Let's add types. So we have this bid and ask currency representing our inputs and outputs from the liquidation. So just parameterize the response using generics, standard language feature in Rust. And the idea is that we're saying this is an integer, but we're constraining its type to be some arbitrary ask currency. Likewise, you can see that this bid currency here has been parameterized. And then in our query message in the input, we parameterize the same thing. So we're basically saying that when we query, we're querying a contract that has this bid denomination and this ask denomination, so that when we input amounts and so on to the liquidation queue, we can have some amount of notion of this is type safety. You have to input an amount in some collateral denomination, and the exchange rate should be something like a bid over ask exchange rate. For example, if you have standard units that we all learn in grade school, the conversion between kilograms and grams and so on, that's a very typed conversion rate. So we want to bring that same type safety from math to our contracts. So if you extend this now from just query messages to executes and so on, you're basically parameterizing your entire contract. And so the idea is that we're not only parameterizing a query message, we're parameterizing some address that represents a liquidation queue and saying, hey, this is a liquidation queue for liquidating Atom and receiving USDC. And we can simulate, we have the notion of some macros that we generate to create these contract interfaces from existing query messages and execute messages. And then you can easily simulate an amount we're inputting. So we're inputting this A denomination of collateral, and this is type checked here. And then we're inputting this rate that converts from A to B, and that's also type checked here because of our strong types. So this is a real kind of test that is from the code base. Basically, you can see that we're getting two Oracle rates. One is from A to USDC, one is B to USDC. This is in a test environment, so these are arbitrarily calculated prices. But using the Oracle feeds on Kujira or any Oracle-enabled chain, you could easily basically retrieve all this information. And these rates are strongly typed, right? So if we try to calculate the rate from A to B now, we have to do this in this order. So if we try, I guess this is the continuation where we calculate using the rate we calculated here. In this currency, we just multiply by the rate, and we automatically get this type hint that now we're in the B currency. So we have some strong notions of type safety here. The problem is that we want to make sure that we have errors if we're trying to do operations that just don't make sense mathematically. So this is done here. If you try multiplying an amount by the opposite rate, so for example here, the end result would be something like A squared over B instead of B, which doesn't make sense because we're multiplying by the inverse fraction, right? So very helpfully, the Rust compiler gives us a type error, and the benefit of this is that we're actually leveraging our programming language to the fullest extent when we're writing our contracts. So likewise, if we try adding two amounts, so A and B, we're trying to add A with B. So this is going back to that example with if you're trying to add US dollars and euros together, we actually do get a real error, which basically says expected A but got B. And so it's a lot stronger type safety, and this has actually caught bugs that we were about to ship to production had we not, obviously implemented testing, but use this library. Now this is all a relatively experimental direction that we're taking CosmWasm. So the idea is that we eventually want to fully type all our contract interfaces. We want to have contract interfaces that not only say, like, we have this message and we expect these inputs as a decimal or as an integer, but we have this message, we expect this amount in this currency, and we expect these funds, as funds right now are relatively untyped in not just CosmWasm, but the Go SDK as well. Obviously, there's some developer tooling that we have to create around this that should be utilized to make it much more optimal. So a couple of other Kujira projects that I could have talked about today, but just did not get the chance to, so we have /onion, which is our replacement for IBC hooks. It's a replacement that basically gets rid of a lot of the difficulties that we have with our present-day IBC hooks, and makes a much more ergonomic version that fits into the SDK much better. Seedless wallet support, we're adding passkey-based authentication, one-click onboarding for users without seed phrases, using the inbuilt trusted enclave on the iPhone and so on for storing these secrets, and I think they're sharded across like iCloud, for example, or Google Cloud. And then we also have a bunch of developer tools, and we're also working on some synchronous interchain query support. All of this stuff is open source, and eventually it is developed eventually with the goal of upstreaming it to the SDK. So if you're working on anything that could benefit from any of this stuff, feel free to come ask, talk to me about it, and I think we'd be happy to chat. Yeah, any questions or anything, I'm available on Telegram or here. Yeah, thank you.
Could you briefly touch on like when you would want to use a macro function?
Yeah, sure. So I suppose I very much breezed over it, but the idea is that we always have our interfaces generated, or not generated, but specified manually, right? We rewrite our contract interfaces as a set of queries and a set of execute messages that the contract accepts. Now the problem is that when we're executing CosmWasm queries, we often have to write like these really huge blocks of code just to execute a query, even though it's already typed. So when we introduce macros, it generates a lot of the code for us. So instead of writing, a WASM query and then you specify the whole execute query message with each argument specified and so on, it would generate like a .simulate function on some Orca object and do everything for us. And because this is all code generation, there's no mistake we could have made manually typing out these interfaces and so on. So that's the idea there, yeah.
Have you guys already, so you use a lot of type wrapping in there, like bring type safety in. Have you guys tried offloading a lot of your verification to like your deserialization layer yet? And
yeah.
If so, have you had any experience or like issues?
Yeah, so this actually all was developed with the goal of zero code on the contract developer side to have all this verification built in. Now the problem is that types are abstract, right? They don't actually represent real values just yet, at least. So when we want to deserialize something into a type, we might be deserializing it like with no information about what the actual, for example, denomination of this coin should be. There's a lot of ways around that I've been looking into, for example, doing some very arguably unsafe things with Rust and so on. But yeah, so the goal is that you just specify all this in an interface and it automatically does all the validity checking and so on, making sure this is the right currency, that you've been sent the right coins or no coins at all at the deserialization time, and zero code on the developer side. Yeah.
Thanks.
Are there any sorry if I missed this, but are you gonna push? Is it worth moving any of these into a shared repo that especially coins related stuff feels like it should just try to be standardized as much as possible?
Right, yeah. So this is all being developed open source, but we're not 100% certain on the final API and so on. So once we get something that we're using internally for our contracts and that works really well, then we can start talking about, upstream it into, for example, some sort of CosmWasm utils library or into the SDK itself, or STD for CosmWasm itself. And because it's providing such strong type guarantees, it makes sense to do this. Yeah. The argument against it is that it makes your code somewhat more confusing for someone who's not used to Rust. And especially since we've been having these conversations about, how can we get more people into CosmWasm, it may not be always appealing, but arguably it is the safest thing to do. Yeah.
Oh, I guess one other are there ways of maybe doing a lot of these checks more at compile time rather than I guess that's what kind of Rust does, I guess. Right?
Yeah. So inherently you're opting into compile time safety checks because you're using types. The runtime part of it comes in when you're instantiating, for example, a order book for a certain pair. Then you need to make sure that you're comparing the right denominations, and that can't be done at compile time because you use the same, for example, WASM binary for each order book. Yeah. Yeah.
Barry?
Hi, Amit. Great talk. I have two questions. One is, are you guys specifically doing this with currencies for now? Is that the main place where you're trying to make the types more restrictive? And then I was curious if you could also give a 30-second overview on Xonion
Sure.
What you guys are doing there.
Yeah. So I'll hit the first part of that first. So we are doing specifically currencies right now, just because in our experience, building half a dozen DeFi apps and 24 contracts, that is the one thing that really is missing in terms of type safety. Everything else kind of just works, and there's no reason to do unnecessary innovation there. But currency is something that we're just treating as strings, or I guess some string type wrapper, and so that's where we saw the actual safety benefits. So speaking about X/Onion, basically how it works is if you're familiar with IBC hooks, you basically put in some encoded actions to take in a memo when you do an IBC transfer. And so this doesn't change that base, format and transfer is still an IBC transfer. You're still specifying things in a memo field, but what you are specifying changes. Instead of saying a contract message or whatever an IBC hook is right now, you basically serialize an entire transaction, including some signer information and so on, into the memo. And so that transaction will be inserted when you receive an IBC transfer into for example, the mempool or into the next block's proposal, and so, or the current block's proposal. And you basically have a full native transaction being executed as a result of an IBC transfer. And so this provides a lot of benefits, most notably, for example, sender spoofing is no longer an issue. And so the main reason that Kujira decided not to implement IBC hooks is because we are a very smart contract-focused chain, right? And contract developers shouldn't have to worry about, is the sender a module address or is it a address on a foreign chain that I can't deserialize correctly? It should be, this is a Kujira account that is submitting a transaction. It should be, felt as basically it was native, if that answers your question there, yeah.
Other questions? All right, thanks, Amit.